this is a fundamental shift in how we think about science. Not entirely correct. In fact, only partly correct. But we give him big ups because the insight was really spectacular. Okay, Niels Bohr. Now we're 100 years ago. He came up with this new concept, brand new concept of how atoms or electrons are distributed around the central nucleus. Okay, so this is important. Because I showed you some ideas last lecture about J.J. Thomson. I'll come back to that in a moment. Bohr goes, no, no, no. Because those line spectra, they knew electrons were involved. So the central question, how are electrons distributed around the nucleus? We know from Rutherford we have a central dense core of neutrons and protons. Where are the electrons? And the atomic spectra was an experimental hint, and Bohr tried to explain it. So here's the insight. So I'll leave this up for a long time. Please listen before you write. The key thing is that he said that electrons in atoms could only be in certain places. And he called those places orbits. And he gave them a second name. He called them stationary states or energy levels or energy states. But there were only certain orbits, only certain states that the electrons could be in. They couldn't be everywhere around the central nucleus. That's another way of saying that the electrons are quantized. That their positions around the nucleus are quantized. This is big. And so now we talk about permitted orbits or permitted stationary states. Okay, so I want to show you what this looks like. Okay, so here's the nucleus. Everybody can see that? Dense. Okay, so what Bohr thought, where we have these orbits. So you can think that's an orbit. And then that's another orbit. And that's another orbit. And he named them. He named them. So this is n equals, this is n equals 3. It's the third farthest orbit away from the nucleus. This is n equals 2. This is n equals 1. And it goes to infinity. In his theory, you could have an infinite number of stationary states. The closest orbit, and I'll show you this in a moment, is the lowest energy orbit. The closer you are to the nucleus, the lower the energy of that stationary state is. Okay, that's important. So there are two things that he's talking about. He's talking about distance from the nucleus and the energy of the orbit. So how does this relate to atomic spectra? I know that's what you're thinking right now. You're thinking, how is this related? And that's a great, great thought. Let's say, so most electrons would like to be at low energy, like you. You like to be at low energy? You do too, if you're right there right now. Okay, so you energize them, you put them in that tube, you move an electron to a higher energy, higher n value state. So you're here. That's what the discharge is. But it's got to come back. So it comes back, it goes like this. So it goes from n equals 3 to n equals 1, and in the process, light is given off. Okay? Now let's say that some of those electrons are in the n equals 2 state. Comes here. Light is given off. Oops. Light is given off, but it's at a different frequency. Oh, I lost it. Yeah, that's too bad. I lost it. Yeah, I lost the whole thing. It's okay. You know, it's okay, because I can do it again. I know. It's a skill that one acquires after many, many years of doing science. Drawing on a board. So here it is. And this h nu is different because the energy is different. Remember? H nu is equal to energy. The energy difference from this, the gap is bigger. So I have a different h nu. That gives the lines. N equals 2, and then the last one is n equals 1. Okay, now, one thing I failed to mention. So I can have an electron here. I've already shown you that. I can have it here. I can have an electron here. Those are all allowed, and this is good. Very, very good. Now, what if I said the electron is here? So in the Bohr model, absolutely not. This is not allowed. This can never happen. It could be on any part of this orbit right here, or that orbit. It can't be between the orbits. There's no possibility of the electron being there. It has to be in these discrete levels, quantized. Quantized. Wait. Okay. I'm waiting. Because he matched his theory to experiment. Hold on, it's coming. Good question, though. So I guess I should say to you, wait. I'll get to you there in a minute. Okay, so I think we've been here. Okay, so this is what I just showed you. Light is emitted, it comes out of the atoms as electrons move from one state to a lower state. N equals 3 goes to n equals 1. N equals 2, n equals 1. N equals 3 to n equals 2. That is what I'm talking about. That gives off energy as light, and you can observe that in the atomic spectrum. And to answer your question, for hydrogen, his theory matched the lines that came off. It predicted where these, we call them transitions from one state to another, occurred. This was unbelievable. The theory predicted the experiment. So each state has an associated energy. So distance and energy, I want you to remember that. Distance and energy. Oh, that sounded like a baby crying. And this worked well for the hydrogen atom. It matched the hydrogen atom well. And so, getting back to the question, which is a good one, and I'll let you write, I'll talk a little bit. There's an important component of the Bohr model that I have to introduce to you. And this is that each orbit has an associated energy, and he came up with a way of predicting that energy. A formula, an unbelievably simple formula. Okay, so let me show you this formula. Are you ready? Okay, good. So here's the formula. He said the energy of any n level, so this is any orbit, is equal to a constant that they knew experimentally called the Rydberg constant. And I'm going to just show it like this, RH. And I'll just write for you. This is called the Rydberg constant. And that constant is times 1 over n squared. And n is the number associated with the orbit. And he called that number the principal quantum number. Oh. Sorry for that line, my thing. So each energy level, each stationary state has an energy associated with it that you can get. The Rydberg constant is in fact what it actually is. It's a constant. I give it to you on the exam. And n is just the n level. So it's all good.
Does
Yeah.
Rydberg have a D in it?
What?
Does it have a D in it?
Rydberg, yes it does. Thank you. I left a space there for you to ask me that exact question. We're working together today. You don't buy that, do you? No, thank you. Yeah, that was pretty lame. Okay. So, getting back, finally now, I'm going to get to your answer. Okay, so there it is. There's the diagram that I showed you now. It's a little clearer maybe because it's more computerized. N is the principal quantum number. You can go any integer value from 1 to big numbers. There is the correct spelling of the Rydberg constant, and there's the value associated with it. Something you can get from a textbook or the front page of my examinations. Now what we can do, you see, what we can do is determine the energy from here, I don't know if this will work, from this point here, it's not working. Oh well, from one higher state to a lower state. And that's what I'm going to show you how to determine that. Oh, I should tell you that n is the lowest energy state. Forgot to mention that. I've already said that. And energy increases as the distance from the nucleus increases. So those are the two key points that I want you to remember. And I think it's important for you to realize, as you write this down, how unbelievably different this is from what other people were thinking. People had a completely different view of it, and I'll show you the view. I'll show you the view. You remember the view, the ugly view. J.J. Thomson, do you remember that picture? Did you write that picture down in your notes? You did? Really? Wow. Good for you. Okay, so I showed you this on Thursday. And so Thomson thought that this is how it looked. That the electrons were somehow floating around this sea of positive charge. So this is very different. Very, very different. But, so I told you that the Bohr model was spectacular at predicting the line spectrum for the hydrogen atom. And it's also just great for the helium ion. Oh. Yeah, the helium ion. And it's also great for the lithium-2 ion. Now, you're going to write this down, and as you're writing it down, what does the lithium-2 plus ion and the helium-1 plus ion and the hydrogen atom, what do they have in common? Now, keep it to yourself. Keep it to yourself. I'm going to ask someone. What do they have in common?
They have one electron.
Absolutely. That's a wonderful answer. Thank you very much. They have one electron. And so it turns out that the Bohr model works spectacularly well for atoms that have one electron. Unfortunately, the things that we really want to work with often, and then some, have more than one electron, and it doesn't work. The Bohr model doesn't work for any atom that has more than one electron. So that's the why. Any multi-electron species, it falls apart. And so it falls apart, so we're in trouble. And so I've told you that these all have one electron, and this just recaps what I said. It says that the Bohr model cannot handle when you have more than one electron because electrons can interact with one another, and there's nothing in the Bohr model that allows you to account for that. And you say, well, I know what you're thinking. Why are you telling me this? Why are you even bringing this Bohr thing up? It's a bore to me. That's what you're thinking. This woman here doesn't like the Bohr model. I did it because historically, it really changed the way we think about the atom and the structure of the atom, the electrons around the atom, and it led to quantum mechanics, which is what we're going to go into next. It led to that.